Hi everyone, welcome back to our next video. In this video I'm going to talk about sound waves. Ultimately what I'm going to do is just talk about the characteristic of waves and how it changes the sound you hear. We're going to talk a little bit about why you hear what you hear. And then I'm going to end the video with a little bit about resonance. And resonance is literally a lesson I teach in my physics and music class for 4 or 5 lessons. So it's a pretty big topic, but I am just going to introduce it and talk a little bit about it for you. Excuse me. Okay, so like I said, we're going to talk about wave and their properties. We'll talk about this thing called natural frequencies as well. And actually I'm going to not talk about the speed of sound. I'll just let you know that we're not going to do that. Okay, so what are sound waves? So talking about waves, they're a disturbance of matter without transport of matter. So we're seeing the energy, right? So what I have here is a tuning fork, and I just happen to have one. That's exciting. And if I strike this, as you can see, even with my pretty good camera, you can't really see that it is moving back and forth. In fact, you can't really hear it. It's really hard to hear. You need something like a table or the wall. Here then, huh? So I'm putting this against the wall. Pretty cool, right? So what you're seeing is those tines actually move back and forth, and what do? They actually push the air, and you can see the air being pushed here, and the air gets compressed, and you see those patterns of compression, and you see these patterns of not compression, which are called rarefactions. Tuning forks make pure tones, so in other words, it's just going to make one frequency at a time. My voice, for example, is not a pure tone. I actually have more frequencies happening at once, which is why everybody's sounds different, right? Even though I could sing my own note like, ah, and you can sing that note, ah. Our physical body shape, size of our throat, what are these called? Vocal folds. All those things actually contribute to why you sound different, called the timbre, which is another lesson. So we actually saw this already, and actually I'm going to come back to it because it's actually pretty cool in that it shows you some of the wave features. So I'm going to go back to the sound. I'm actually going to put it on wave mode for now. One thing I do want to show you is what happens when I change 2 attributes, the frequency and the amplitude. Frequency changes how frequent your wave is, right? So in other words, if I make this higher, you'll see more waves happen at once. And there you go. You can see the spacing is smaller because there's more waves. And if I do this, the spacing is larger because there's less waves. Hopefully that makes sense. But now I'm going to play the tone. You're going to hear what this sounds like. So notice the low frequency versus high frequency, right? This is a high frequency wave, and that's a low frequency wave. So now what I'm going to do is put this right in the middle. And I know this is going to be a little annoying, but I'm going to leave it there for my point. I'm going to change the amplitude. Okay, so I'm going to put it really low. So I hope you notice the amplitude changes the loudness, right? And notice that we're looking top down at this picture right here. So if you notice that it's top down, you can see the fact that the waves are not really oscillating very much. I don't think, it says it has a side view, but the side view I don't think is really helpful. So we're looking top down. But if I make big waves, right, those waves will be really big. So they'll have really big crests and troughs. So you can see the wave changes, right? You see these dark and short lines like that. So you can see the big and small ones that are happening here. Amplitude changes the volume. Frequency changes the pitch. And in fact, that's my next 2 topics after I talk about that it's a longitudinal wave, sorry. We talked about this before, but it's longitudinal. And that sound is also a pressure wave. So your microphones actually measure wave pressure, not actual frequency. And that's because we have these patterns of pressure, right? We can see it. Now, when we model sound waves, this is actually what sound waves look like, but what we do is we model compressions as crests and rarefactions as troughs. So high pressure, low pressure. So that's what this diagram is. So even though this is what it actually looks like, we'll always describe sound waves like this, as highs and lows. And sound does need a medium because it's a matter wave. So our eardrum does that and measures pressure. So the reason why is if you ever notice you go in a pool and sometimes your ears feel funny because you have more pressure on your ears, or if you go on an airplane, your ears feel funny, there's less pressure of your ear. So your ears measure pressure. Now how many times it goes back and forth is how it interprets frequency. So your brains are so cool, right? So it doesn't actually hear those things. It measures it counts vibrations, and that's how you interpret pitch. So that's what this is showing you here, your eardrum. And then, as you might imagine, as it hits the red, it's being pushed. And then as it's hitting the refractions, it's actually getting sucked out. So it's in and out. It's a weird kind of thing that's happening here. And like I said, when you have space, you will not have any sound waves. So, like the Death Star exploding with these, big sounds, that's not actually going to happen. So just like I explained with the demonstration, frequency is to pitch. So frequency is the physical feature, something that we can measure. The pitch is what we perceive. So pitch is high or lows. And the frequency of the wave changes it. So a high-pitched wave looks like this, and a low-pitched wave looks like this. So that's how they physically look if you were to look at the physical feature and the perceptions of what you actually hear. And then the amplitude does the volume, how loud and soft it is. So it all has to do with energy, right? So if I talk like this, it's much louder than if I talk like this. It takes way more energy to scream. So especially if I talk a lot, all day, if I'm teaching for a long day, I actually get physically tired. It takes a lot of energy to talk all day. Trust me, I've been doing it for many years. But it takes energy. So, and you can think about it, if you're going to scream, it's not easy to do. In fact, if you're I don't know when you've screamed for a while, but if you had to, you get tired afterward. It's the energy of the wave, but that's the volume. So when you change the volume knob on your radio, look what it does to the wave, right? It doesn't change the frequency. Notice that it still has 3 bumps here and 3 bumps here. It changes the size of that amplitude. The internet's great. I found this in the internet, and a bird talking and screaming. It's hilarious. Okay, so this is a great multiple choice question. Which one is louder and which one has higher pitch? So I'll give you a second to think about this. Okay, there's a couple seconds. So I hope you noticed that B is higher pitched because it has more waves than A. But in terms of amplitude, they actually look the same, right? So my argument would be, in fact, I would say they're the same loudness. So it'd be this one and this one without a change in volume. That would be my guess here. Same thing. You should be able to look at the wave and know if it's louder, softer, higher, and lower, just based on the wave shape. So, the human hearing range is by definition 20 hertz to 20,000 hertz. If it's not in that range, we can't hear it. This is unfortunate because I love doing this in class. This is what we do. We do a hearing test. I'm going to go ahead and show you that website. Sorry. There we go. So, what we do is in class is we play these notes. So they're pretty high pitched. Woo-wee, right? And actually, you start to drop out. So I actually start dropping out about 15,000 hertz. So I'm going to do a hearing test on myself. Okay, I can hear it today. Now, the sound wave actually goes in and out. When the sound wave starts going in and out, it sounds loud and soft. That means you're at the edge of your hearing. Let's see if I can hear 16,000. Nope, I can't hear that. I'm gonna do it again. That's so weird. I can't hear it. Can you hear it? Probably. Most of you probably can. Nope, I can't hear it. I highly suggest you go to this website and do your own hearing test and see where you drop out. So when you do, you don't hear it, although it's actually playing a sound. It's like a dog whistle, right? You're playing a note that you can't hear, but other animals can. So this is a fun activity I love to do in class. So to be honest, not many people actually hear up to 20,000. Your hearing goes mostly wear and tear. So many people have different hearing ranges. And we also in class do 20 hertz too. We like to go all the way lower, which is a fun thing to do. If you're outside of the hearing range and you're above 20,000, that's called ultrasonic waves. And if you're below the hearing range, that's called infrasonic range. So ultrasonic uses ultrasound, as you kind of get from the name. It uses sound waves that are higher than the human hearing. And what happens is that the sound waves gets blocked by certain tissue and goes through other tissue. So when the sound wave comes back, it can make an image. And the best thing about sound waves is they're not invasive at all, and you could use them and they're not harmful. So that's why they're really good for imaging. And there seems to be animals that hear in that range, like whales and elephants. So this is the different ranges of animals in terms of how they speak. And you can see that, we hear our instruments pretty fine. We hear, this is what we hear. But you can see right here the ranges of other, like I said, instruments and animals. So bats, dolphins, and this one was a new one, crickets, makes sense, are all out of our hearing range. And this is just another diagram of that. I'm not testing you on this. This is just interesting information. This is animal hearing frequency range. So in other words, animals like bats and dolphins can hear outside of our range. Pretty crazy. Look at all this. All cool information. The whale is in infrasonic range, and mostly the crocodile can hear pretty much similar to a human. That's pretty interesting. And then the bird and etc. So it's just some interesting facts about hearing. So resonance. Resonance is a very interesting phenomenon that happens in science. I'm going to talk about it and then give you a ton of examples. So resonance means to basically take one object and set it in motion. And if the second object is identical in frequency, that second object will go on its own without actually being struck at all. So I have a demonstration for that. So I'm going to go to, what am I going to? MIT resonance demonstration. I would do this in class once again. Fortunately, this is what we have. So here's a tuning fork demonstrating resonance. So what we have here are two tuning forks, and they're on blocks so you can hear them better. And that weight attachment will actually change their pitch. So here we go. You can hear that it strikes the single tone right there. But notice how that one actually started ringing without being struck. So he's going to demonstrate that by striking this. And notice that this one is also playing without being struck. That is resonance. Is even though the second one didn't get struck, it actually matches the vibration. Its natural frequency wants to vibrate at that speed. So anytime it picks up on that, it's going to vibrate on its own. Now he's going to show you now that it won't work if you change the frequency by putting that weight attachment to it. And there you have it. So it doesn't work because you don't have the second tuning fork at the right frequency. So that's a very physics example of this. I have some other examples. I have my Google Photos here. Here is an example of resonance. So this is my husband. He wanted to be in the video. But this is when you take the glass and you start striking it. And notice that he dipped his finger, so I'll rewind it so you can see it. It's a good one, right? So that is resonance, because what happens is as your finger slips over the top of that rim right there, you cause it to vibrate at the same wavelength as this air column right here. So it's pretty cool. Is it this way? Yeah. So then we like to have a little fun. So these are all, again, classroom demonstrations I would do. So I'm going to pour the water. So watch what happens. So notice that, right? Notice when the air column decreased, the sound wave pitch also decreased, right? Because the air column got, the size of the wavelength got squished. And then you can... Pretty fun, right? We were laughing when we did it. We're like, okay, if you ever need a sound wave of an airplane like diving down, we got it for you. But like I said, a very fun thing. So another example of resonance is swinging on a swing, which is kind of crazy. Instead of a sound wave, it's a pendulum. So if you think of like, you know, your pendulum lab or something like it, you're sitting on a long string, right? So what happens is as you pump your legs, you're matching the frequency of that swing. And when you do, in this case, the amplification comes into the angle. So you go larger like this. Remember, amplification with sound is loudness. So things get louder when you have resonance. To resound, the amplification, dramatic amplification occurs. Yep, I did that. So another crazy, here's a bad example of resonance, right? Those other ones I'll call good. So what happened was the Tacoma Narrows Bridge in 1940, the frequency of the wind matched the natural resonance of the bridge and actually collapsed. It's pretty wild. Good news, bridges don't do this anymore because they're accounted for resonance. It's a very important physics concept that we study pretty extensively. So, but anyway, this is when resonance, there's too much amplification, too much vibration, and it can actually physically break things apart, which is the same kind of concept with bringing, you know, a wine glass with your voice. So same concept, if you sing it with the right resonance at the right frequency, you can break a wine glass, it's true. I'll leave you to watch the YouTube video on it, but this is another example of resonance, and this is when it's bad, too much amplification happening there. Now resonance happens in all sorts of instruments. This is how instruments work. I'm not going to go in extensively in all of these, but it does occur on strings, such as guitars, violins, and like a harp, for example. You did a standing wave lab, or you're going to do a standing wave lab at some point, like the one in the picture right here. But there are other instruments like the flute and the human voice and the pipe organ. They're all pipes, so you can create standing waves there. And you can even create standing waves in drum heads and in something solid like a piano. So another cool video is the Chladni plates. And same thing, you can get resonance in these standing waves. So this is somebody hooking up a speaker to a two-dimensional plate, and they put rice on it, and the vibrations. I'm going to skip him talking it. But what you're seeing here is the vibrations, right? When it's vibrating the most, there's no salt there. And when it's not vibrating, there's salt and it collects there. So these are what we call nodes and antinodes. So you can actually see waves on two-dimensional places. Yeah, this one's better.
Where there's wonder,
After this ad, oh boy.
joy will follow. Wonder, feature joy. Jackie, you know it?
Oh my goodness.
Tell me why you're here.
Okay, finally. There you go. So you can see all different patterns happening. It's really kind of cool stuff. And you see that how it changes the shape, right? Now, the important thing to know is that it only happens at certain frequencies or resonant frequencies, right? So you can have multiple standing waves on an object as long as it's the right frequency. I'll do one more. Cool, huh? So that one's a cool one. I like that one a lot. So one thing of resonance that happens is these things called standing waves. So standing waves happen when you create different harmonics or different wave patterns on the same wave. Now we call them harmonics because we can make different wave patterns that create standing waves. Now if you're music or do music, they actually call these overtones, so they're slightly different and they actually work on a slightly different mechanism. In terms of naming, that is, but these are also used in music as well. But we get different ways to create these standing waves. Now, standing waves happen when you have two waves that are trapped in the same medium and they interfere with each other. And when they line up perfectly, see if I can do this right, they line up perfectly, they get louder, and when they are, well, when they line up perfectly, we call that an antinode. And when they are against each other like this, we call it a node. So they cancel. So when the waves cancel, you get these nodes right here, spots where it appears to be not moving, standing. And we got these places called antinodes, where the two waves add up and appear to be larger. Now the black wave is the standing wave that I'm talking about. So notice the black wave, we have these red dots, these places where the wave stands still. Now, the red and the blue is supposed to show you the incoming wave and the outgoing wave happening at once, incoming and outgoing. In fact, I could show you my guitar. Okay. You're not going to be able to see the standing waves. They just happen very fast and very quickly. So you won't actually see the vibration, but you can create a standing wave on this. And what happens when you do is that the wave goes back and forth between the nuts of the guitar, and the wave comes in and out and repeats itself. So the nodes are actually at the ends of the guitar, and the antinode is right in the middle. The second harmonic comes if I put it, if you look back on this screen, if I put my finger right in the middle of the string, this is the second harmonic. So the first harmonic, second. Notice the change in pitch. See? There we go, I figured it out. So this is the first harmonic, second, third, fourth, and then the fifth. There we go, like that. So I'm creating different standing waves on my guitar by placing a node in different locations. So standing waves are very hard to create if it's not the perfect condition. The perfect conditions include the right frequency, amplitude, and speed. Good news is the wave speed on guitar stays the same. The frequency usually stays the same because I don't change the length. And the amplitude usually stays the same speed. So do not confuse antinodes with troughs and crests. Antinodes occur because of interference, and crests and troughs occur because the wave is happening on its own. There's no second wave. There's no interference. So a lot of people get these confused when we do this. So antinodes are not troughs and crests, because standing waves happen when two waves interfere, where a trough and a crest doesn't happen. I'll put a star with that, with interference. So like I said, the features of a standing wave are nodes and antinodes. Okay, so nodes are these black dots right here. I have 1, 2, 3, 4, 5, 6 nodes right there. And those are the places of the wave that don't move. So if I were to walk on this wave, I would actually stay still on that. And then the antinodes are the big parts of the wave. So I have 1, 2, 3, 4, 5 antinodes. Now notice I didn't count the bottoms. You don't need to count both top and bottom. This whole spot is an antinode. I don't actually, I know why, because they have the blue line right here, and then they have the red line right here. So that's why they do that. So you'll definitely do some counting of nodes and antinodes. Love you too, honey. So you can also create standing waves in air as well. Everything froze. There we go. And you can see the node and the antinode in air, right? So here's the node, the dot's not moving, and here's the antinode. You can see that it's moving back and forth, right? And notice the displacement, right? The node is right here, and then the antinode. So this is the same as creating an creating a standing wave in like an air pipe, so like a flute or a clarinet, for example. So, I'm just going to quickly take a quick peek here. So what I'd like you to know with standing waves is how to identify the harmonics. So I'm actually going to take a quick trip back to our standing waves on strings. So these are our standing waves on strings specifically. And I hope you notice that if you count antinodes, right? One antinode, you get the first harmonic. And notice here, 1, 2. 2 antinodes is the second harmonic. Or you can count the loops. That's another thing that people have done. 1, 2, 3 loops. That's the third harmonic, etc. Now, I want to show you that pipes work a little differently. Again, I want you to just recognize their patterns. If you put a wave in a pipe, what happens is if it's open on both sides, like this one, you get antinodes. And then in order to create a wave pattern, you have a pattern of antinodes and nodes. So for an open pipe, the patterns look like this. You have an antinode, node, antinode. That's the first harmonic of an open pipe. The second harmonic looks like this. So notice that we have a loop now. And then the third harmonic. So in this case, when we're counting harmonics, we're counting nodes. First harmonic, 1 node. Second harmonic, 2 nodes. Third harmonic, 3 nodes. That's different than waves. On strings, we counted antinodes. For open pipes, we count nodes. Now we can have what is called a closed end. So notice one end is closed and the other end is open. And we get different wave patterns from this. So notice the wave patterns. At a closed, there's an error here. My thing is not, it's got to be charged, I'm sorry. But this is actually a closed end, so please make note in your notes. I'm going to fix the slides and re-upload them. But this should be closed and this should be open, because in a closed pipe, there's always a node. And then, if you notice here, node, node, antinode, etc. So these are the first 3 harmonics of a closed pipe, but if you notice, they're a little different, right? In fact, this right here is 1/4 of the wave, and this is 3/4, and this is 5/4. So for these, they actually have a slightly different pattern to them. So I do want you to be able to recognize them. We're not going to do any calculations or anything regarding their frequency and all that fun stuff. But I do want you to recognize these. I think what I'm going to do for this part is actually I'm going to skip this part because I usually talk about this in class a little more detail. Well, I guess I won't skip it. I'll just quickly go through it. So I know a lot of you are medical majors, which is why I talk about resonance and MRIs. But I hope you noticed that magnetic resonance imaging has to do with resonance. Now, it has to do with magnetic resonance, which is kind of fun. So what happens is that water has these things called moments, and what those moments represent are their north and south. They're like little compasses. So just like you can magnetize a paper clip. Paper clips are not magnetic naturally, but if you put a magnet next to it, it sticks to it. That's because you align their magnetic moments. So if you put a strong magnetic field in the presence of something that can be aligned, you can make something magnetic. In this case, when you do MRIs, it's water that does this. Now, when it happens, what happens is that these moments don't actually go straight, they precess. So when they actually are spinning, and they spin like a top. So they can actually get this precession frequency, and that frequency can be measured. It's pretty wild, right? And then what they do is they match that precession frequency. And when they do, they actually change their magnetic moment direction. So notice how they're flipped right here. And when they're flipped, they get a signal. Turns out that if you have something like a tumor, you get more signals in one spot than another. That's how we can detect tumors. And that's like a very simplified view of MRIs. I usually have a demo to show you, and it's a little hard for me now to do that. But a very basic, surface level understanding of MRIs. They use resonance by matching the natural frequency of the precession of water molecules. Got that? This was I didn't talk about this, but that's okay. I'm going to skip this too. Don't worry about this slide at all. Okay, and that's everything about sound that I'm going to cover for this lesson, and let me know if you have any questions. Thank you.